All right, folks, continuing on here in Chapter 5, Section 5.3, we're gonna analyze what second derivatives can tell us about graphs of functions. So our section objectives, the first objective is we're going to compute these things called higher order derivatives. They're pretty friendly. Then we're going to determine intervals of concavity. That will allow us to then locate inflection points. And then we're going to apply inflection points and interpret its meaning in a special situation in the business world. So we know the first derivative, f prime, tells us when the function f is increasing or when it's decreasing. Now the second derivative, and there's the notation for the second derivative, f, I read that as f double prime. That tells us when the function f prime increases or decreases. So in short, the second derivative tells us the behavior of the first derivative. It's the exact same relationship that exists between f prime and f. The exact same relationship exists between f double prime and f prime. Okay, now we use that notation, which is read f triple prime, to represent the third derivative. But if you want to get higher derivatives, such as the fourth derivative, you kind of put the numbers in parentheses. So to find higher order derivatives, you're just going to differentiate repeatedly until the required derivative is reached. So let's do a quick example. For the following functions, we're going to determine the first three derivatives for each function. So we're going to determine the first derivative, the second derivative, and the third derivative. So write it down because I'm heading off to the chalkboard to work through this example. Hey folks, this example we're asked to find the first three derivatives of the given functions. So the first one, the function is 4x to the fourth minus 7x cubed plus 8x minus 9. So remember, it's just repeated differentiation. So the first derivative is 16x cubed minus 21x squared plus 8. Differentiate that, that will give us the second derivative, which is 48x squared minus 42x. And then differentiate the second derivative to get the third derivative, which is a 96x minus 42. So these higher order derivatives, nothing more than just computing derivatives of derivatives, etc., etc. Part B, the function we were given was g of x equals natural log of x cubed. I decided for this one I'm going to start off with the step of algebra. I'm going to use an old property of logarithms that allows me to rewrite natural log x cubed as 3 times natural log x. Then we get the derivative. Well, the derivative of natural log x is 1 over x. So the derivative is 3 over x. Also keep in mind 3 over x. I'm going to write that in parentheses right here. I can rewrite 3 over x as 3x to the negative first. And that actually helps me in getting the second derivative. That would make the second derivative negative 3x to the negative second, or negative 3 over x squared. And then the third derivative, well, the third derivative is just the derivative of the second derivative. So here's the second derivative. So the third derivative is 6x to the negative third, or 6 over x cubed. And that's it. That's all there is to finding higher order derivatives. So let's head back to the slides and see what we are going to do with higher order derivatives, in particular the second derivative. All right, you can see finding higher order derivatives is not that difficult. It's just doing derivatives of derivatives. We started the section by saying that the second derivative gives us information about the first derivative.
So let's head back to the chalkboard, and I want to analyze this just a little bit more. So here we go back to the chalkboard.
All right, folks, in section 5.1, we saw how the first derivative, f prime, could tell us the behavior of the function f. So what I have up here on the board is the graph of a function, its derivative, and its second derivative. So the function is 1/3 x cubed minus 4x plus 2. The derivative of the function is x squared minus 4, and the second derivative is 2x. So a quick review from section 5.1. Remember, wherever the derivative is positive, the function is increasing. So look at the graph, and where the derivative is positive, so it's positive from negative infinity to negative 2, and it's positive from 2 to infinity, that's where the function was increasing. And where the derivative was negative, and here the derivative is negative from negative 2 to 2, the graph is below the x-axis, the function is decreasing. That same relationship exists between the derivative and the second derivative. I mean, notice that the second derivative is positive on the interval 0 to infinity. Let me write that down. Second derivative is positive on the interval 0 to infinity. That matches up exactly with where the derivative is increasing. The derivative is increasing from 0 to infinity. Let me write that down. The derivative is increasing. Likewise, the second derivative is negative from negative infinity to 0. So for x is from negative infinity to 0, the second derivative is negative. And that matches up exactly with where the derivative is decreasing. The derivative is decreasing from negative infinity to 0. And, let me write that down. So it shouldn't be a surprise that the same relationship exists and how the second derivative can tell us the behavior of the derivative and the graph of the derivative. Now let's head back to the slides to see why it's going to be important to know where the derivative is increasing and where the derivative is decreasing.
All right, so what we saw at the chalkboard is, where the second derivative is positive, that tells us where the derivative is increasing. Where the second derivative is negative, that tells us where the derivative is decreasing. The exact same relationship that existed between derivative and function. It's the same concept. So just to practice this a little bit, we're going to determine the second derivative, and we're going to use it to determine where the derivative is increasing and decreasing for the function, well, f of x equals x to the fourth plus 4x cubed minus 48x squared plus 10x plus 6. So we have our function. We're going to compute the second derivative of this function to tell us where the derivative of the function would be increasing or decreasing. So get this written down, get it into your notes because I'm heading off to the chalkboard to work through it.
All right, we just kind of summarized back on the slides that where the second derivative is positive, the derivative is increasing. Where the second derivative is negative, the derivative is decreasing. And so here, in this example, we're asked to use the second derivative to determine where the derivative is increasing and where the derivative is decreasing. And that's the function. We're given the function x to the fourth plus 4x cubed minus 48x squared plus 10x plus 6. So we need to get the second derivative. So here we go. The first derivative is a 4x cubed plus a 12x squared minus 96x plus 10. The the second derivative, well, that's the derivative of the first derivative, so that's a 12x squared plus a 24x minus 96. So just like what we did in section 5.1, we're gonna make a sine diagram. So we need to get the critical values for the second derivative. And remember, critical values, we've got to see where it's 0 or undefined. Since it's quadratic, it's defined everywhere. So we just need to determine where does the second derivative equal 0. And in trying to factor this, the first thing I would do is take out the common factor of 12. That leaves me with an x squared plus x minus 8. And let's see, hopefully that factors. Hopefully this trinomial factors. X, sorry, I forgot a 2 here. Makes the factoring, it's going to work now. When I take a 12 out of 24, I would end up with a 2. So the combination to try is 4 and 2 plus 4 minus 2. It checks. Set each factor equal to 0, and we get those values of x for where the second derivative is equal to 0. So we make a number line. We're going to do a sine diagram just like we did in section 5.1. Put these values of x on the number line. So negative 4 and 2. And here I'll put second derivative, derivative. It's just like section 5.1. The only difference, second derivative, derivative. And it's the sign of the second derivative that's going to tell us if the derivative is increasing or decreasing. So pick a number in the interval negative infinity to negative 4. I would pick negative 5. Toss it into the second derivative to see what comes out, a positive or a negative. So I look at the factored form like I did in section 5.1. This would be negative. Negative 5 comes in for x. This factor is negative. This factor is negative. So positive times negative times negative. Positive, derivative increasing. In the interval negative 4 to 2, I would pick 0. So when I put 0 into the derivative for the x's, I'd have a positive times negative. That's negative, decreasing. And then out in the interval 2 to infinity, I would pick 3. Positive, positive, positive. So positive times positive times positive is positive. Increasing. So I can now write down that the derivative is increasing on the interval negative infinity to negative 4, union with 2 to infinity. And the derivative is decreasing on the interval negative 4 to 2. So now we're building up to something on why we need to know where the derivative is increasing and decreasing. So let's head back to the slides and see what's next.
All right, so now we know how the second derivative tells us about the graph of the first derivative. The second derivative tells us where the derivative is increasing or decreasing. But the second derivative can also tell us something about the graph of the original function. Specifically, this definition. If you have an open interval AB where the function is differentiable, if the derivative of the function is increasing, then we say the graph of the function, well, it's said to be concave up. If the derivative is decreasing, then we say the graph of the function, well, it's said to be concave down. So, I mean, concave up kind of looks like a cup. Concave down kind of looks like a frown. So here's a quick picture. What you see in blue would be like the graph of the function itself. And one thing I'd like you to remember is notice on concave up, I've sketched in like 2 tangent lines. When the graph of a function is said to be concave up, tangent lines to the curve, tangent lines to the graph of the function are going to be below the curve. Whereas when it's concave down, tangent lines would be above the curve. So we should be able to string together stuff that we have analyzed so far. So here's what I mean by that. We know where the second derivative is positive. That tells us where the derivative is increasing. We've just seen in a definition that where the derivative is increasing, that tells us where the graph of the function is concave up. That's what I mean by stringing stuff together. Likewise, we know where the second derivative is negative. That tells us where the derivative is decreasing. And where the derivative is decreasing tells us where the function is concave down. So now because we've kind of strung all this stuff together, we can actually condense this down significantly and have the second derivative just immediately tell us something about the function itself. And that gives us the test for concavity. So for a function f who has a second derivative on interval ab, if the second derivative is greater than 0, if the second derivative is positive, then the graph of the function is concave up. So second derivative positive, graph of the function is concave up. Notice how we're condensing down the first string that we have at the top of this slide. If the second derivative is negative, then the graph of the function, well, it's concave down. So second derivative negative, function concave down. So let's practice this. We're going to determine intervals where the graph of that function is concave up and where it is concave down. And we're going to see how we use the second derivative to tell us this. And we're also going to use a sine diagram. So get this example written down because I'm heading off to the chalkboard to work through this one.
All right, folks, we just finally seen why we need to know where the derivative is increasing and where the derivative is decreasing, because that matches up with what is called concavity. And we saw in our test for concavity, the key on the test for concavity is wherever the second derivative is positive, the function, the graph of the function is concave up. Where the second derivative is negative, the graph of the function is concave down. So in this example, you're given this function and you are asked to determine intervals where the graph of the function is concave up. That's my shorthand symbol for concave up. And where it is concave down. That's my shorthand symbol for concave down. So the key on finding intervals of concavity is to get the second derivative. So for the function, we can't get the second derivative without first computing the first derivative. So there's the first derivative. So the second derivative is 12x minus 16. And then it's very similar to what we did in section 5.1. We want to determine where the second derivative is undefined and where the second derivative is equal to 0. Well, since it's a linear function, it's a type of polynomial, it's linear, it's defined everywhere. So the only candidates will be where the second derivative is equal to 0. So we set the second derivative equal to 0 and solve for x. And we get 16 over 12, which, by the way, I'm going to reduce that down to 4/3. And just like we did in section 5.1, we make a sine diagram. So there's my number line. I'll put 4/3 on the number line. my bookkeeping, put second derivative here, and I put function there. Because it's the sign of the second derivative that's going to tell me the concavity. So, just like you did before, the interval negative infinity to 4/3, pick a number that you know is definitely in that interval. I would pick 0. Toss it into the second derivative to see what comes out, positive or negative. So when I put 0 into the second derivative, a negative number comes out. So negative tells me the function is concave down. Likewise, in the interval 4/3 to infinity, pick a number that you know is definitely in that interval. 2. I know 2 is in that interval. Evaluate the second derivative at 2. So when we evaluate the second derivative at 2, a positive number comes out. So positive. That tells me the graph of the function is concave up. So to answer the question, determine intervals of concavity, the graph of the function is concave up on the interval 4/3 to infinity, and it's concave down on the interval negative infinity to 4/3. And that's it. Second derivative tells us concavity. Now there's something that's happening here at the x value of 4/3. Notice at this x value of 4/3, the graph switches or changes its concavity. It changes from concave down to concave up. So let's head back to the slides real quick to see what the significance of that is.
All right, folks, in that last example, we determined intervals of concavity for the function. And you may have noticed that the function itself, at an x value of 4/3, the concavity switched. The concavity changed. The graph would have changed from concave down to concave up. So any point on a graph where the concavity changes has a special name. It's called an inflection point. You know, very quickly, I'd feel bad if I didn't mention this. The x-coordinate of an inflection point is a critical value for f prime. But let's look at how we are going to determine how we locate inflection points. I mean, the last example really kind of illustrated exactly how we locate inflection points. We're going to find values that I'm saying x equals d, where the second derivative is 0 or where the second derivative is undefined. And then we're going to put those values on a number line and make a Sine diagram. And if we see concavity changes, we have an inflection point. So let's practice this. Let's determine intervals where the graph of that function is concave up and where it is concave down. So we'll be making a Sine diagram. And that Sine diagram will tell us where, if anywhere, there are inflection points. So write this into your notes because we're heading off to the chalkboard to work on it.
All right, we just saw that a point where a graph switches or changes its concavity is called an inflection point. So in this example, for this function, we were asked to determine intervals where the graph is concave up, where it's concave down, and to locate any inflection points. So remember, the concavity question requires you to determine the second derivative. So here we go. The first derivative is 3x squared minus 12x plus 6, which means the second derivative is 6x minus 12. So we need to determine where the second derivative is 0 or where the second derivative is undefined. Second derivative is defined everywhere. So where does the second derivative equal 0? Well, that occurs at x equals 2. So we make a Sine diagram. Put f double prime there, f there. And the interval negative infinity to 2, I would pick 0. I'm tossing it into the second derivative to see what comes out, positive or negative. So I toss 0 into the second derivative and negative comes out. That means concave down. The interval 2 to infinity, I pick any number I want, so I pick 3. Evaluate the second derivative. So I'm going to evaluate the second derivative at 3. Positive comes out. So that means concave up. So to answer the questions, the function is concave up on the interval 2 to infinity. The function is concave down on the interval negative infinity to 2. So the graph switches concavity at x equals 2. So that means it has an inflection point at an x value of 2, but it's a point, so we need to know the y coordinate. So it has an inflection point. To get the y coordinate of the inflection point, we're talking about a point on the graph of the function, so we have to evaluate the function at x equals 2. So put 2 in for the x's, and you'll see that the inflection point is 2, -7. All right, let's head back to the slides and see what's next.
All right, it's not too bad finding intervals of concavity and inflection points. So here's another example. Determine inflection points for the graph of this function. And in fact, this is one I want you to do. I want you to pause the video. I want you to work through this example. And then once you've done this example and you think you found inflection points, restart the video and I'll be at the chalkboard working through it. And I'll give you a hint. There are 2 inflection points.
All right, folks, we went back to the slides and I asked you to do this example where you're asked to find the inflection points for this function. I gave you a hint that there were 2 inflection points. So hopefully you tried it, hopefully you listened, you paused the video, tried it, and here we are seeing if you got it correct. So inflection points. Well, we only know inflection points if we know intervals of concavity, which means we need to get the second derivative and make a sine diagram with the second derivative in the function. So let's see, the first derivative is 4x cubed minus 3x squared minus 6x minus 4. The second derivative is 12x squared minus 6x minus 6. The second derivative is a polynomial, so it's defined everywhere. So the only thing of interest will be where the second derivative is equal to 0. And my first step in trying to solve this would be to factor out a 6. And I think of this factors, 2x here, x here, minus 1 plus 1. Yep, that's the correct factorization. So I set the factors equal to 0 and I get, see, x is -1/2 and x is 1. So I come over here, making my sine diagram. I put those numbers on the number line, -1/2 and 1, f double prime and f. And then I go through the process, pick a number in the interval -infinity to -1/2, toss it into the second derivative, see what comes out, positive or negative. So I pick a -1 here. I toss -1 into the second derivative. I looked at the factored form of the second derivative. Positive, see, that would be negative, negative. So positive times negative, positive. The graph would be concave up. The interval -1/2 to 1, I will happily pick 0. Toss 0 back into the second derivative to see what comes out. So let's see, that'd be positive. This factor, if x is 0, that would be positive. That factor's negative. So positive times negative is negative. So it's concave down. And then finally the interval 1 to infinity, I would probably pick x as 2, positive. This factor would be positive, and that factor would be positive. So even though we weren't asked, or I didn't ask you in this example to determine intervals of concavity, you know the intervals of concavity. And you can't determine inflection points unless you know those intervals of concavity. So we see at the x value of -1/2, the graph switches concavity, and at an x value of 1, the graph switches concavity. So there are two inflection points. First one, x is -1/2, and the second one, x is 1. And we need to find the y-coordinates. So if I put -1/2, remember I have to go back to the function. I have to toss -1/2 back in here for the x. As a decimal, you would get 6.4375. You could write that as a fraction. 6.4375 is 103/16. When you put 1 in for the x's, what comes out is -2. So, 2 inflection points. Hopefully you found them both. Let's head back to the slides and see what's in store for us.
All right, hopefully you were able to work through that last example and find inflection points. I'd like to look at a quick summary of what the derivative and the second derivative tells us. So this is a table that you would find in the book. If the derivative, if I'm looking at the first row here, if the derivative is positive, that tells us the function is increasing. If the second derivative is positive, that tells us the function is concave up. And so the graph would have that kind of shape that you see there. But what it really tells me is the derivative positive tells me the function's increasing. The second derivative positive tells me the function is increasing at a faster rate, or it's increasing at an increasing rate. Whereas, now look at the second row, if the derivative is positive, we know we're still increasing, but if the second derivative is negative, then we're concave down. And, the graph would have a general shape like what you see there. And so what the derivative being positive and the second derivative being negative tells me is that the function is increasing, but it's increasing at a decreasing rate, or it's increasing at a slower rate. Its rate of increase is slowing down. Likewise, you can look at the third row and the fourth row, but I just wanted to highlight this table real quickly because it kind of leads into the last thing we're going to look at in this section. There's some business applications, inflection points. Well, they have a special name. They're called points of diminishing returns. In your text, example 6 and the text that follows example 6 illustrates that the inflection point is the same as the point of diminishing returns. So what I thought we would do to finish off this section is, in your book, I thought we would do exercise 64 on page 338 to practice finding the point of diminishing returns. So make sure you get your book open, look at exercise 64, because I am heading off to the chalkboard to do it.
All right, number 64, after we did a little bit of hopefully reading that I asked you to do, we're seeing that in some business applications, an inflection point can be thought of as a point of diminishing returns. And so in number 64, you were asked to find the point of diminishing returns and interpret what it means. So we have to get the inflection point, which means we have to know intervals of concavity, which means we need to know the second derivative. So let's get the derivative. See, the derivative is, that's a negative 15 halves x squared plus 225x plus 150. So the second derivative is negative 15x plus 225. That's defined for all values of x, so we just need to determine where it equals 0. So set it equal to 0 and add 15x to both sides and then divide both sides by 15, and I think you'll end up seeing x is 15. So we make a number line. We're going to make a sine diagram. So on this sine diagram we put 15 plus 2 more values of x. I mean, this function is saying x is between 10 and 30. So I need to put 10 and 30. So that tells us we don't care what's happening for x is greater than 30. We don't care what's happening for x is less than 10. So there's the second derivative in the function. I pick a number in this interval, 10 to 15. I'd probably pick 11. I evaluate the second derivative at 11 to see what comes out, negative 15 times 11 plus 225. And what comes out is a positive number, which tells me the function would be concave up. In this interval, I can pick any number I'd like. I'd probably pick 16. Evaluate the second derivative at 16. Negative 15 times 16 plus 225. That will be a negative number. So I do see concavity switches at an x value of 15. It's an inflection point. So the inflection point, and here it's the point of diminishing returns. So I'll write it down like that. The point of diminishing returns is 15, and then the y-coordinate is found by evaluating the original function at 15, and oh good grief, you get like 29,125. So what does this mean? What is the point of diminishing returns? It's an inflection point. The graph changes from concave up to concave down. So it goes from concave up to concave down. So it's actually telling us, and you should have read this, that it's the point for this problem. It's the point where the greatest growth, and I think that was a sales function, the greatest growth in sales. So it's the point where the greatest growth in sales is occurring due to advertising. I believe X was representing advertising dollars. So folks, that's it for number 64. That's it for section 5.3. Everything you needed to know about what second derivatives can tell you about functions and their graphs. How second derivatives tell you intervals of concavity, which in turn tells you inflection points. So at this time, you're good to go. You can do the exercises here in section 5.3. So go do the exercises in section 5.3. Thanks for watching.